In-keyboard analog pointing devices, a case for the pointing stick. We are all familiar with office text editing using a mouse and keyboard. At IBM T.J. Watson Research Center, we are experimenting with alternatives to the mouse. This video describes our ongoing work concerning pointing devices for use with computer keyboards. We have been focusing on mixed keyboard and pointing tasks. Here a person is using our pointing stick with a standard mouse-oriented text editor. The alternation of pointing and entering text is typical of many uses of computers. It is this class of task which motivates our work on in-keyboard pointing devices. Notice that Ted is not taking his eyes off of his work to find the mouse or keyboard. The pointing device is already within reach. He does not need to take time away from his work to move his hand. In this video, we will show devices we have been experimenting with. We will compare our pointing stick to a mouse. We will present an argument for the pointing stick, and we will describe our ongoing research on improving the performance of the pointing stick. The post that you see Ted resting his finger on to move the cursor was made in our laboratory. Here, Joe Rutledge is fabricating a pointing stick. It is a steel rod with two miniature semiconductor strain gauges bonded to flats near the base. The gauges measure lateral force applied at the top of the rod. Our initial idea was to put the pointing device directly under a home key for the extremely dexterous thumb or index finger. This would allow the user to avoid moving their fingers at all from a touch-typing home position. This was accomplished with the J-pointer pointing device mounted under a J key on a keyboard. Notice the four cantilever arms, each instrumented with a strain gauge sensor. When the key is depressed, these report torque applied to the keycap without interfering with its normal use for typing. The user must signal his use of the J key for pointing rather than typing. We arranged a mode switch signaled by a momentary depression of the left shift key with no other concurrent key. Taking the time to change modes and remembering to do so imposed a noticeable cognitive load. Exploring alternatives, we considered the space below the space bar, above the keyboard, and settled on the space between the G and H keys. The pointing stick extends slightly above the level of the keys. The G to H space is never traversed by a touch typist. The protrusion is small enough to avoid being brushed by other users. We have installed J-pointers and other pointing devices in IBM XT, AT, RT, PS2, and in other vendors' keyboards as well. This experiment, similar to the classic card English burr work, was used to compare various pointing devices. In this subject-based experiment, a target is presented at a random position and size. The subject moves the cursor to the target and presses the button as quickly as possible. If we plot several hundred such shots with the fit's distance size difficulty index on the x-axis and time on the y-axis, for our pointing stick we get this time versus difficulty plot. For a subject using a mouse starting each shot from the keyboard, we get this time versus difficulty plot. While the regression line is rather different, note that except at the extremes, the point clusters are very similar. Note also that the mouse would take longer if we included the time needed to return to the keyboard. For a subject using a mouse starting each shot already holding the mouse, we get this time versus difficulty plot. Note the 0.6 of a second difference in time between the two mouse cases. This suggests that for tasks in which keyboard use alternates with pointing, the pointing stick is at least equivalent to the mouse. The comparison would clearly favor the pointing stick if we included the time for repositioning the subject's hand on the keyboard at the end of each shot. For pure pointing tasks, however, the mouse still outperforms the pointing stick. Now we will show how we are working to improve the pointing stick. In a second evaluation experiment, we set up a maze of numbers which a user selects in numerical order. The target is a single character in each case. The arrangement and order of targets is designed to give a randomized sequence of direction and distance selections. Before data is recorded, subjects do a number of trial runs to learn the target sequence. By varying the relationship between force on the pointing stick and cursor velocity, we have been able to improve subject speed in time trials. Here, the x-axis shows force on the stick. The y-axis shows cursor velocity. We found that reducing sensitivity for near-zero forces allows users to do fine positioning more quickly. We were at first surprised to find that restricting the maximum speed of the cursor increased the overall maze run speed. This allowed eye tracking and improved control. With our improved force-velocity relation, we have been able to reduce overall maze run time from on the order of 35 seconds to under 25 seconds. Ongoing research includes exploring more precise experimental paradigms for helping us understand these questions. Important issues have motivated us to consider in-keyboard pointing devices. A user must take their eyes off their work, causing a shift of attention to shift their hand back and forth to a mouse. Mice require desk space which might not be available in laptop computers, busy desks, or non-office settings. Other problems with non-office settings impinge on the usability of a mouse. As well as training issues, physical and safety considerations may preclude the use of a mouse. In this video, you have seen several aspects of our ongoing research on in-keyboard pointing devices. We have shown how we build the devices and why we find the pointing stick interesting. We have demonstrated this device to be at least as effective as a mouse for some tasks. We have also shown you how we are working to improve the performance of these devices.